So now I'm going to talk about how to do calculations involving polyprotic acids. If you'll remember, I told you at the beginning that as long as our K values were far apart from each other, I could treat polyprotic acids as just a collection of monoprotic acids. And so I'm going to prove that to you right now by working our way through a titration. This may seem like an odd thing for me to take all the time to do, is to do something as complicated as a titration, but I think if you see it play out, you'll appreciate what I'm talking about when I indicate to you that polyprotic acids are just monoprotic acids. Proof of that will be the fact that the calculation you will do will involve one of our simple monoprotic acid problems. All of this, though, hinges on the fact that my K's have to be far apart. So guess what? I'm going to let my K's be equal to 4 and 10, kind of like I'm doing carbonic acid. And now I'm going to go ahead and I'm going to add some hydroxides here. Now in step 1, no hydroxides are added. This is the beginning of a titration. So all I have is H2A. Well, what is H2A? H2A has a pK value of 4. It's just a weak acid. How do you do this calculation? This is a weak acid calculation. H plus is equal to Ka1 times the concentration of the acid to the 1/2. So if this was 1 molar H2A, then the pH would be 2. I ignore the pK associated with the second association, so it's so weak, so it contributes very few protons. So I have a very simple, quick answer. It's just KaCa to the 1/2. So far, so good in working my polyprotic acids. Let's work step 2. I'm going to add 1 hydroxide. When I add 1 hydroxide to solution, I immediately form HA minus. So there's my HA minus. What do I have in solution now? I have an HA minus and an H2A. Well, that's a weak acid, and that's a weak acid missing a proton. That makes it a weak base. That's an acid and its conjugate base. An acid and its conjugate base, that's a buffer. This is a buffer problem. Therefore, H plus is equal to Ka1 times Ca over Cb, and since I've got equal amounts of these, my H plus is equal to Ka, so my pH is equal to 4. My goodness, this is just as easy as when I was working a monoprotic problem. I just had to make up my mind to ignore the second K value. So I've got through step 1, which was a weak acid problem. I got through step 2, which is a a buffer problem. Let's go on to step 3. Step 3, I'm going to add 2 hydroxides to it. And when I add a second hydroxide, it's going to look like this. I've got HA minus left and HA minus. So what do I have? All right, here goes. That's a weak acid. And weak acids can lose protons, so I must have to do some sort of Ka2 weak acid problem that involves this. But I know some of you are saying, now you're playing favorites. Why don't you add a proton to this? Can't this add a proton just as well as it loses a proton? Haven't you shown us a problem in which HA minus, which is what this species is right here, there's HA minus sitting right there. It can go to the right and be an acid that loses a proton. It can go to the left as a base. There's actually a famous name we give to this kind of species, one which is a switch hitter, one which can go either way. And the answer is that it's amphiprotic. You can always tell an amphiprotic species. It's got a negative charge on it, suggesting that it's base-like, and it's got a proton on it, suggesting that it's acid-like. The point is, you don't know which direction it's going to go. It can be either a Ka1 problem or a Ka2 problem. Turns out mathematically, although we don't have to derive it in here, you can make approximations which split the difference and say that the H plus concentration is simply equal to the Ka1 times the Ka2. It multiplies together those two values and takes their square root. This is the first new calculation, and last, by the way, that I am adding to our collection, our tools available for doing acid-base calculations. I showed you the strong case. I showed you the weak case. I showed you the buffer case. Now I'm showing you, finally, the fourth case, the amphiprotic case, the one that arises when you're doing polyprotic acids and you have something which is a switch hitter that can add protons, that can lose protons. The beauty in this is that it's an incredibly simple calculation. I waited to get to the point where I have the simplest calculation of all. I just add the the pK values together and divide by 2. The answer is 4 plus 10 is 14 divided by 2 is equal to 7. The pH is equal to 7. Notice that I have done a polyprotic acid problem calculation, not just a polyprotic acid, but a titration of it. And every bit of math I'm doing is simple as can be. The weak acid case, the buffer case, the amphiprotic case. Let's add another hydroxide. Adding a third hydroxide here. Not surprisingly, I'm back to a buffer region where I've got an acid and its conjugate base. The difference is that this is the acid and conjugate base not associated with the Ka1 but with the Ka2. If you're confused about it, just look up here and you'll see it. There's the Ha minus and the A double minus. There's the HA minus and the A double minus. That's the one that involves, oh look, Ka2. Notice how it's different than this one right here. This is the H2A and the HA minus. The H2A and the HA minus, that involved the K1. So this one is the buffer for the Ka2. This is the second buffer region. H plus is going to be equal to, well, evidently, Ka2 times Ca over Cb. These are equal in volume or in amount. Therefore, the pH is equal to the pK. The answer is 10. I can't believe it. I've gotten through 4 different calculations. A weak case, a first buffer case, an amphiprotic case, a second buffer case, and I haven't had to lift a finger to do anything hard mathematically. Why? Because my diprotic acid, because the Ks are far apart, is just a bunch of monoprotic acids with that one simple amphiprotic case exception.